Right, that's where we are. So what I'm going to do now is, see, the squared is happening to this whole thing, isn't it? It's like a binomial. It's two terms being squared. So I can't use that formula again. What I'm going to do is I'm going to expand it out. I'm going to multiply it out. All right? So I'm going to be taking 1 minus cosine of 2 beta t times itself. 1 minus cosine of 2 beta t plus, why am I, y'all should, okay, so where did I had it right here, right? This is the first time I wrote it minus. I apologize. Thank you for pointing that out, not letting me get too far with that. Yes? Okay, now expand this. So this to this, this to this, this to this, this to this. You should get 1 plus 2 cosine of 2 beta t. Okay, so that's, you get the 1, and then you're going to get 2 cosine beta t as you put them together. 2 cosines of 2 beta t, I should say. And then what's my last term?
Cosine squared.
Plus cosine squared of 2 beta t, like that. And that's where we are, right? That's what's there? Mm-hmm. The good news here is that they're separated, right? 3 different things, and I should be able to address them individually. So let me write that down now. We have 1/4 integral, okay? We have 1 plus 2 cosine of 2 beta t, and then we have plus cosine squared of 2 beta t, and then all of that dt. So looking through those, Scott,
Yep.
You caught up? Are you still writing?
I'm still kind of writing.
Okay, I'll let you write a little bit while I erase. We all good with this expansion? Okay. Okay.
Sorry.
Yeah, no, it's okay. So now we can look at these individually, can't we?
Yeah.
Okay, so here we're just going to find the antiderivative of 1 with respect to t, right? Which would just be
Which is dt.
just t.
Or t.
Just t, right? Now, can we find the antiderivative of cosine of something?
Yes.
Yes, right? That the antiderivative of that has to do with sine, right?
Yeah.
So we should be able to handle both of these. Agreed, everyone? Okay, but what about this one, Scott? See this
That one-
squared?
No, probably not. So would you have to like multiply that out, or?
Well, if we're looking at this as like this is our new little universe, right? Because we can handle these two.
Yeah.
But if this is our new little universe, how do we handle cosine squared? How do we handle cosine to an even power? Yeah, we do what we just did,
Yeah.
right? We do what we just did again because it's cosine to an even power. So we're going to have to use that formula again. Make sense? Okay. So let me continue here. I'm gonna do what you said for me to do. Well, I'm gonna take a little more time. I'm gonna do this, just so you can see really kind of mechanically what I'm doing here. dt. All right, I'm off camera, but that's okay. So what I've done here is I've separated this up into 3 separate integrals. All right, we're going to do 1/4 times the integral of that, plus 1/4 of the integral of that, plus 1/4 of the integral of that. Make sense, everyone? Now let's go ahead and just knock these out. This one and this one, let's just figure out what those answers are. So the first one, we said the answer would be what?
T.
Just t, but then 1/4, right? So we're going to have 1/4 t. Okay, and then this one, you're going to have to be careful on this one. You have 1/4, oh, you have a 2 there, right? These are going to reduce anyway, but okay, so now let me see here. Marissa, you're up. Marissa, I'm already accounting for the 1/4 and the 2. So you just need to give me the antiderivative of cosine 2 beta t.
1 over 2 beta
1 over 2 beta
sine
sine of
2 beta
2 beta t. What do y'all think? Well, remember, 2 beta is a constant, right, in front of the variable. So if you find the antiderivative cosine of that, you have to scale it by 1 over the constant. And 1 over the constant would be 1 over 2 beta. Yes? No? What's wrong? You look like you're disagreeing. I don't want to point at you, but what's wrong? That's not? So if you take 1 over 2 beta sine of 2 beta t, and I ask you to take the derivative, okay? Take the derivative. This is a constant, right? So it's just going to come for the ride. So I'm going to take derivative of this. Okay, derivative of sine of something is cosine of it, right? But then times the derivative of what's inside with respect to t, which means that there's going to be 2 beta. Do you agree with that? 2 beta, and then these are gone. So you get cosine 2 beta t, which is this part. I told Marissa to ignore that, right? I said just ignore that for now. You believe? You a believer? Yes? Everyone believe? Okay. So that's that part. So we've got this done, we've got this done, and now we need this one, right? But because we got cosine squared even power, we're going to have to use the power reducing formula. So my next piece here should be, let's see, plus 1/4 integral, and then let me see who's up. Hogan? Okay, so how can you use the power reducing formula to rewrite cosine squared of 2 beta t? So this one right here. So I want you to use this one right here.
Yes, sir. So
1/2
1 plus cosine
drum roll
4 bt.
4 beta t. Good. All you're doing is doubling the argument. That's what that formula does. It allows you to pull the power down, but you got to double the argument and do some other stuff. But the main thing is that your argument doubles. So that 2 beta t, you multiply it by 2, you get 4 beta t. And then close this off dt, right? And now you have 2 separate terms in here, right? And you should be able to do these individually because the antiderivative of 1, we've got that. And then the antiderivative cosine of something, we should be able to do that. So we no longer have any powers, we should be set, all right? So I think I'm ready for the last line here. This should be the last line. And there will be one more line after this. 1/4 t plus, let's see what happened here. We got 1 over 4 beta sine of 2 beta t. And then plus, let's see here. Should I do the 1/4? Let me do 1/8. How about that? 1/8. That's me I'm bringing that out here so we're not looking at that anymore. And then antiderivative of 1 would be t, because it's with respect to t. And then plus, and let's see here. Okay, Kim, since you kind of mentioned it last time, antiderivative of 1 is t. So Kim, what would the antiderivative of this be then? 4 beta. And then, so that takes care of the scaling of the constant, but now you just need, what's the antiderivative of cosine? Sine. So sine of 4 beta t, like that. Plus c. Is it a mess? Is it messy? Is this a long problem? And welcome to Cal 2, all right? This is just the nature of the beast, okay? All right, I'm still not done. Well, you know what? Yeah, okay, I'll just write it. 1/4 t plus 1 over 4 beta sine of 2 beta t plus 1/8 t plus 1 over 32 beta sine of 4 beta t. That beta thing sure does mess things up, huh? Yeah. Okay. Okay, so all I did there is distributed the 1/8 through here. Anything else we could do? Combine like terms. There's two terms in here that can go together. These two right there. 1/4 t and 1/8 t is going to give you 3/8 t. Right? That's the only other thing you could do. Is put those two together. You can't combine these two together, right? Because they have different arguments inside the sine. So that's how we handle even powers of cosine. How would you handle even powers of sine? You use this formula instead. So you're just going to have a minus in there instead of a plus. Everything kind of works the same way. There is a problem. Let me double check it in the book. There is a problem in the homework for 6.2. Where is it? Yeah. Well, I guess, oh yeah, there it is, number 10. This is a problem that if you do it, when you do it, because you're going to try it, right? This is what we call torture. Okay, this problem is torture because it's so tedious and long. Like you're probably going to wind up having to turn your page sideways and write this way to keep everything on one line. Because what happens here is you have cosine squared theta cubed. And then what you have to do is rewrite that using that formula and then cube it. Cubing a binomial gives you a lot of stuff. And then each one of those, well, just go enjoy this, okay? I work it out on video in my homework solutions if you get stuck. Every Calculus 2 student should suffer through this problem, just so you can say, I did it, all right? And then once you do it, you don't need to do this. I don't recommend you do this, but you can appreciate how adding an 8, like putting that as an 8 would just be a monster, just a monster. So the book doesn't go to 8. I won't go to 8. I won't give you something like this on the test, all right? It's too long and tedious. But something like I just did right here is something you could see, all right? Yes?
You said on the test we're only going up to 6.1 or 6.2?
Yeah, the test is when? Tuesday? Is it Tuesday or is it?
Yeah, Tuesday.
It's Tuesday, so a week from today. Yeah, and we're stopping at 6.1, so this will not be on it. Unless y'all want it on it. I mean, it doesn't matter. It doesn't matter. I mean, we can put it on it or we can not. It's your call. No? Okay, so that means there'll be more on the next test. Yeah. All right, so I wish I could like somehow have like little gauges next to each of y'all to see like how y'all feel. I wish I had that ability to see how you feel about things, you know. You have to get in there and do the problems, right? That's what you have to do. And that's why I put those homework solution videos on there. I mean, to help you learn. Don't just watch them. Don't just watch them. You have to try the problem yourself and then use the video as a guide to help you, right? If you just watch them and go, yeah, sure, I could do that, then you'll just get stuck when it comes time to the test. All right, there's still more. We still have 10 minutes. So what if we have integrals involving tangent and secant? Okay, so far we just looked at sine and cosine. What about tangent and secant? Well, if we have tangent and secant, let's talk about what we already know. We know the antiderivative of secant squared x, right, is tangent x. We know the antiderivative of secant x tangent x is secant x. That we know. So it's not as clean and easy as sine and cosine, right, with tangent and secant. We also know that if you saw any sort of linear expressions in here, you'd have to scale out by that. Okay, so that's kind of like this underlying theme that we have with all functions now. So what's the strategy? Well, what if you see an integral where you've got tangent to a power and secant to a power multiplied together, where the power on secant is even? Well, if you see that, then you're going to use the Pythagorean identity for secant. Now, I don't have them up here. What are the, let's see. We're not going to have time to work through these. Okay, let's show of hands. How many of you know? Well, I'm not even going to ask. Everyone knows that, right? Everyone knows that one. So there's two others, right? So show of hands, how many of you know the others just by heart? It's okay if you don't. The two others, no? Okay, how many of you know how to get the two others without looking at a formula sheet? You know how? Okay, how do you do it?
Divide by sine all the way.
Okay, so if you know this one, you can generate the other two just by doing something simple. First one, you're going to divide everything through by sine squared. Okay? So if I divide this by sine squared, what do I get?
1.
Okay. What if I divide this by sine squared?
Tangent squared.
You get cosine squared over sine squared, which is cotangent squared. And then here you'll get, what did we divide by? Sine? 1 over sine squared would be the same as, what's 1 over sine? Cosecant. So that's cosecant squared, right? So that's one of the Pythagorean, the other ones. Now, how do you get the other one? Divide everything, go back to this one, divide everything by cosine squared. So sine squared over cosine squared would be tangent squared, and then plus cosine squared over cosine squared, 1, and then 1 over cosine squared is secant squared. So those are the other two Pythagorean identities. You can generate them yourself as long as you know this and as long as you remember that little thing. Does that make sense to you all? But you have them on your formula sheets, so you'll never be without them. But if you're ever stranded on a desert island without a formula sheet, you got it, right? We know how often that happens. So what do you think? Should we? We're not going to have time for one of these. So what I think I'm going to do is I'm going to skip to, I think in a few minutes I can look at these very special ones. So look at these three integrals. I'm going to go through these quickly. First one, integral of tan x. Okay, we know the derivative of tan x is secant squared, but what's the antiderivative? And I told you at some point I would go through this, right? Okay, it's time. So what I'm going to do first is I'm going to rewrite this as sine x over cosine x, right? And now all I'm going to do is a basic u sub. I see something in its derivative. What's the something? Careful. What's the something? Cosine x. Why not sine x? Because the derivative of it would be down in the bottom. You don't want that, right? So if I let u be cosine x, the derivative of that is negative sine x dx, right? And I'm off by a sign. I positive sine x dx, I need, right? So negative du equals sine x dx. Okay? Let's rewrite the problem. This becomes negative because of this integral. The sine x dx is accounted for, right? So all I have is the cosine on the bottom. So that's 1 over u du. See how that just rewrites? And what's the antiderivative of 1 over u? Natural log. So this is going to be minus natural log of the absolute value of u plus a constant. But u is cosine. So we get negative natural log the absolute value of cosine x plus c. Now if you look on your formula sheets, you will not see this formula. So someone look on the formula sheet, it says the antiderivative of tangent. Tell me what it says. ln secant of u. I'm going to use x because we're using x. They're saying this. We said this. What happened? properties of logs, right? Property of logs. Remember, if you have a power, there's a property of logs to this. If you have x to some power r, let's say, that you can rewrite this as r natural log of x.
Yes.
Well, we can take this negative 1 and we can push it up here on the cosine. And then it becomes, so I kind of skipped a step here, but this would become natural log of basically cosine of x to the negative 1. Not to be confused with the arc cosine. We are raising cosine to the negative 1. That is not the inverse function. It's just 1 over cosine, isn't it? And that's secant. So that's how their formula looks different than ours. Okay, so you could actually do this same method for cotangent. You could do the same thing. How about this next one? This next one is really nice. This will be the last one of the day. Okay, so last one is this one. So maybe you're thinking this. Yeah, I mean, does that seem reasonable to do it that way? Yeah, you're not going to get anywhere with that. All right, you don't have like a basic U sub. Okay, there's no integration by parts. It's gonna work here. All right. So this is an example of a problem where someone did have to like suffer for a while and figure this out. All right, and check out what works. Okay, check this out. So do you all agree that any expression you're ever given, you can always multiply by 1? Okay, so check out this crazy ass 1 I'm about to multiply by. I'm going to take this, I'm going to multiply this times secant x plus tangent x over secant x plus tangent x. Now that just seems ridiculous, right? That this would do anything for us. But let's just see what happens. So the secant here can get distributed, can it?
Yes.
Okay, so that can become secant squared x plus secant x tangent x over secant x plus tangent x dx. Okay. Does anybody see it now? What you can do? Anyone? What about it?
Use that as the secant x, tan x. Can you use that for substitution?
Basic U sub with U being the what?
No.
The denominator?
Yes, sir.
The whole thing. Do you all see that? If you let U be the denominator, what's the derivative of this? What's the derivative of that? Secant x tangent x plus what's the derivative of that? Secant squared x. That's what's up there. Right? So if you let U be the bottom right now, the derivative of that, du, is exactly what we have on top. It's in a different order, right? But it's the same thing. So what is, do y'all see that? Okay, so what does this integral become? Integral of 1 over u du, right? Because all of this up top, in this, that's du. And then this on the bottom is u. So all we get here is 1 over u du. So integral 1 over u du. And that's natural log of the absolute value of u plus a constant. But what's u? Secant x plus tangent x. That's 1. Yeah, so yeah, you'd never come up with that on your own, right? I don't think. I don't know. Yeah. Yeah, it'd take a while, right? Okay, so what is your homework? Definitely make sure that you're comfortable up through 6.1, right? Next class, I'm going to do a review, but it's not going to be the kind of review you want to have. It's going to be me just reminding you to do your homework and, you know, maybe tell you about how many problems to expect, but there will not be like a formal handout review. All right? So do your homework. Make sure you're comfortable up through 6.1. If you're going to start 6.2, then you can only do so much of it. So let me tell you how far you could go on 6.2. Really, you can't really get past 16 on 6.2. That's all stuff that involves sine and cosine. After you get past number 16, you start to get to the tangents and secants, and we just haven't talked about those yet. So remember I said 6.2 is 2 sections? We're like halfway through the first part of that section. All right, everyone, have a great day. Try and keep these.
Excuse me first.
Yes.
Is there any way that I could retake or